Today we're going to continue graphing quadratics, but this time we're going to graph quadratics in vertex form. Before we start, let's take a look at this recap. Here we can see that a quadratic function has the form of ax squared plus bx plus c. A can never equal 0, and the graph of a quadratic function is U-shaped and it's called a parabola. The lowest or highest point on the graph is called the vertex, and the axis of symmetry is the line or the vertical line that cuts straight through the vertex. All of this is info that you should know. We've learned it in the past, but here it is again. And if we look at the graph, we can see that the vertex of both of these graphs is graphed right there. I plotted the point in orange, and the axis of symmetry is this line that divides each of these parabolas in half. So previously we learned how to graph a quadratic in standard form, but today we're graphing in vertex form. So it's the same function, it looks a little bit different, and it has some different properties as far as graphing goes. Graphing in vertex form requires the use of transformations, which we used in Unit 2. So when we shift the graph left, right, up, down, reflect it across the x-axis, or shrink, stretch, whatever the value of a might be. Here you see vertex form. Sometimes vertex form can be easier, but you do have to pay attention. There is a subtraction sign in the middle of this function, x minus h. This is always going to be subtraction. So this here goes back to Unit 2 of where we were identifying a right or left shift, and you had to kind of think of it of the opposite, because if we had a positive number, it was technically a negative. That would give you a positive value. So anyways, just be careful of that negative sign. But what we really need to talk about here is your axis of symmetry. Previously, in standard form, your axis of symmetry was found by x equals negative b over 2 times a. In this case, the axis of symmetry is just equal to whatever your value of h is. But again, remember that subtraction sign. So if it's x minus h, then your h value is actually positive. So much easier there, you're just identifying one single value for your axis of symmetry. And your vertex is always h comma k. So also a little bit easier. For this first set of examples, you have functions and you're asked to identify the axis of symmetry and the vertex. Number 1 is in the form of 2 times x plus 3 in parentheses squared minus 6. So this first one is one to pay close attention to. Because of this plus sign, that's technically x minus negative 3 in parentheses squared minus 6. So your h value is negative 3 and your k value is negative 6. The axis of symmetry is always found by x equals h. In this case, it's x equals negative 3. Your vertex is h comma k. Here we have negative 3, negative 6. Number 2, this one's already in standard form, so we can see our h value is 2, our k value is 8. From here, we know that our axis of symmetry is always at x equals h, or x equals positive 2, and our vertex is at h comma k, or 2 comma 8. So in vertex form, finding these two terms, or finding the equation of the axis of symmetry and the point of the vertex, tends to be much easier because all you have to do is identify two values, h and k. Because we're graphing these functions using transformations, this right here goes all the way back to Unit 2. This is the same part of the note sheet you saw in Unit 2. We're just going to quickly go through this, review what the parent function of a quadratic is. So the parent function is always x squared. That's your most basic function, and from there it shifts around the graph. Recall that your 5 critical points are at -2. When you substitute -2 into x squared, -2 squared is 4, -1, 1, 0, 0, 1, 1, 2, 4. And your parent graph appears to be U-shaped in the coordinate plane. From this graph, we can see that the domain is negative to positive infinity, and the range is from 0 to positive infinity. The domain never changes. It is always negative to positive infinity. The range does change. So it changes with the graph. So in this example, our increasing intervals are going to be from 0 to positive infinity. Our decreasing intervals are from negative infinity to 0. Remember that you're always using x values, and you're always using round brackets or parentheses. The end behavior on this graph, both ends go up. So the end behavior is as x approaches negative infinity, the function is approaching positive. I wrote that the opposite way, sorry. I usually start with positive infinity. As x approaches positive infinity, the function approaches positive infinity. As x approaches negative infinity, the function still approaches positive infinity. Lastly, our x and y intercepts. The x-intercept in this graph is 0, 0, and the y-intercept is also 0, 0. So this is all the information for the parent function. All of this changes except for the domain when we graph our new functions. So we're going to use the parent function and we're going to perform transformations. You had all of this information back in Unit 2, but a quick reminder, if you have an h value, your h value is going to be your left or right shift. If h is positive, it's going to the right. If h is negative, it's going to the left. If you have an a value, that's a stretch, shrink, or reflection. If you have an a value, you multiply all your y values by a. And if a is negative, it reflects across the x-axis. Lastly, your k value. If k is positive, the graph shifts up. If k is negative, the graph shifts down. You always perform the transformations in this order. So you start with your horizontal shift, then you do your stretch, shrink, or reflection, and then you do your vertical shift. So in this order, starting on the left side, horizontal, stretch, shrink, reflection, and then vertical shift. Okay, save this table, make use of it. Hopefully you remember these rules from before, but here they are again. Okay, for the first set of examples, we're graphing the quadratics in vertex form. We're going to start by graphing our parent function. Our parent function never changes. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Okay, from here we need to look at our transformations. So the first transformation I'm looking at is going to be my shift right here, my h value. Because it's x minus, 3 is actually a positive value. So the first thing I'm going to do is shift right 3 units. That means I take this graph, I shift every point to the right 3 units. And the last thing that I do is my k value. This would be down 2. Take every point, shift it down 2 units. This blue graph is your final answer. You can either leave your other points in your other graphs or you can erase them. Whatever you do, I just need to see your final graph. So I need to see what I have up here as this blue line, and I need to clearly see that that's your graph. For the last part of number 1, we need to identify the axis of symmetry and the vertex. So recall that the axis of symmetry is always going to be found by x equals h. And in this example, your h value is 3. So we can say that our axis of symmetry is at x equals 3. And let's check this on the graph. If we were to graph the axis of symmetry at 3, does that cut right through our blue graph? Yes, it does, so that's good. Our vertex is always found by our h value and our k value, so h comma k. In this example, our h value is 3 and our k value is negative 2. We would write our vertex as 3 comma negative 2. And just check on the graph, does that match? Yes, it does. So we're all set with our vertex. Number 2, y equals 2 times x plus 1 in parentheses squared minus 3. To start with, I'm going to graph my parent function. And then I'm going to identify my transformations. The first transformation I have right there is going to be a left shift. That's the first thing that I do. We're shifting to the left 1 unit. Next, I need to identify my vertical stretch. I'm stretching this graph by a vertical factor of 2. If I'm stretching by 2, I multiply all y coordinates by 2. That means I look at this purple graph up here. This point is at negative 3 comma 4. If I multiply the y coordinate of 4, so negative 3 comma 4, if I multiply the y coordinate by 2, because I'm stretching it by a value of 2, I would regraph this point at negative 3, 8. This point right here is at negative 2, 1. If I multiply 1 by our stretch of 2, 1 times 2 is 2. 0 times 0 is 0. 1 times 2 is 2. 4 times 2 is 8. This green graph is the second transformation, which is a vertical stretch of 2. And then lastly, we have a k value of negative 3. So the third step is to shift down 3. I take the green graph, that was the last one I used. I shift everything down 3 units. And that blue graph is my final answer. I'm actually going to erase everything else here because it looks a little congested. I need to check for my axis of symmetry and my vertex. The axis of symmetry is always your h value, so x equals the h value. In this case, h is equal to, because it's positive 1 and standard form is x minus, this is technically x minus negative 1. Therefore, our axis of symmetry is at negative 1. We can check that on the graph. Negative 1 is right here. That is correct. And our vertex is always found by h comma k. Our h value is negative 1. Our k value is negative 3. So vertex is at negative 1, negative 3. We need to check this on the graph. Negative 1, negative 3 is correct. So this is our final vertex. Okay, I'm going to do these first two on your own problems and you can follow along. And then the other page, or the last page, you can access the answers on the note sheet posted on my website.